Friends, welcome to Coursalence. In this video, we will learn basics of programming. We are all familiar with the computer's ability to perform a wide variety of tasks. For instance, we can use it to play games, write a letter or a book, perform accounting functions for a company, learn a foreign language, listen to music on a CD, send a fax, or search for information on the internet. How is this possible, all on the same machine? The answer lies with programming, the creation of a sequence of instructions that the computer can perform, we say execute, to accomplish each task. This sequence of instructions is called a program. Each task requires a different program. To play a game, we need a game-playing program. To write a letter or a book, we need a word processing program. To do accounts, we need an accounting program. To learn Spanish, we need a program that teaches Spanish. To listen to a CD, we need a music playing program. To send a fax, we need a fax sending program. To use the internet, we need a program called a web browser. For every task we want to perform, we need an appropriate program. And in order for the computer to run a program, the program must be stored, we sometimes say loaded, in the computer's memory. But what is the nature of a program? First, we need to know that computers are built to execute instructions written in what is called machine language. In machine language, everything is expressed in terms of the binary number system, ones and zeros. Each computer has its own machine language and the computer can execute instructions written in that language only. The instructions themselves are very simple. For example, add or subtract two numbers, compare one number with another, or copy a number from one place to another. How, then, can the computer perform such a wide variety of tasks, solving such a wide variety of problems, with such simple instructions? The answer is that no matter how complex an activity may seem, it can usually be broken down into a series of simple steps. It is the ability to analyze a complex problem and express its solution in terms of simple computer instructions that is one of the hallmarks of a good programmer. Machine language is considered a low-level programming language. In the early days of computing, 1940s and 50s, programmers had to write programs in machine language, that is, express all their instructions using ones and zeros. To make life a little easier for them, assembly language was developed. This was closely related to machine language, but it allowed the programmer to use mnemonic instruction codes, such as add-in names for storage locations, such as sum, rather than strings of binary digits, bits. For instance, a programmer could refer to a number by sum rather than have to remember that the number was stored in memory location 1,011,101,101,011. A program called an assembler is used to convert an assembly language program into machine language. Still, programming this way had several drawbacks. It was very tedious and error-prone. It forced the programmer to think in terms of the machine rather than in terms of his problem. A program written in the machine language of one computer could not be run on a computer with a different machine language. Changing your computer could mean having to rewrite all your programs. To overcome these problems, high-level or problem-oriented languages were developed in the late 1950s and 60s. The most popular of these were Fortran, a formula translation, and COBOL, Common Business-Oriented Language. Fortran was designed for solving scientific and engineering problems that involved a great deal of numerical computation. COBOL was designed to solve the data processing problems of the business community. Solving a problem on a computer involves the following activities. 1. Define the problem. 2. Analyze the problem. 3. Develop an algorithm, a method, for solving the problem. 4. Write the computer program that implements the algorithm. 5. Test and debug, find the errors in the program. 6. Document the program. Explain how the program works and how to use it. 7. Maintain the program. There is normally some overlap of these activities. For example, with a large program, a portion may be written and tested before another portion is written. Also, documentation should be done at the same time as all the other activities. Each activity produces its own items of documentation that will be part of the final program documentation. Define the problem. Suppose we want to help a child work out the areas of squares. This defines a problem to be solved. However, a brief analysis reveals that the definition is not complete or specific enough to proceed with developing a program. Talking with the child might reveal that she needs a program that requests her to enter the length of a side of the square. The program then prints the area of the square. Analyze the problem. We further analyze the problem to ensure that we have the clearest possible understanding of it. Determine general requirements such as the main inputs to the program and the main outputs from the program. For more complex programs, we would, for instance, also need to decide on the kinds of files that may be needed. If there are several ways of solving the problem, we should consider the alternatives and choose the best or most appropriate one. In this example, the input to the program is the length of one side of the square and the output is the area of the square. We only need to know how to calculate the area. If the side is S, then the area, A, is calculated by this. A equals S times S. Develop an algorithm to solve the problem. An algorithm is a set of instructions that, if faithfully followed, will produce a solution to a given problem or perform some specified task. When an instruction is followed, we say it is executed. We can speak of an algorithm for finding a word in a dictionary, for changing a punctured tire, or for playing a video game. For any problem, there will normally be more than one algorithm to solve it. Each algorithm will have its own advantages and disadvantages. When we are searching for a word in the dictionary, one method would be to start at the beginning and look at each word in turn. A second method would be to start at the end and search backwards. Here, an advantage of the first method is that it would find a word faster if it were at the beginning, while the second method would be faster if the word were toward the end. Another method for searching for the word would be one that used the fact that the words in a dictionary are in alphabetical order. This is the method we all use when looking up a word in a dictionary. In any situation, a programmer would usually have a choice of algorithms, and it is one of her more important jobs to decide which algorithm is the best, and why this is so. In our example, we must write the instructions in our algorithm in such a way that they can be easily converted into a form that the computer can follow. Computer instructions fall into three main categories. 1. Input instructions, used for supplying data from the outside world to a program. This is usually done via the keyboard or a file. 2. Processing instructions, used for manipulating data inside the computer. These instructions allow us to add, subtract, multiply, and divide. They also allow us to compare two values, and act according to the result of the comparison. Also, we can move data from one location in the computer's memory to another location. 3. Output instructions, used for getting information out of the computer to data and variables. All computer programs, except the most trivial, are written to operate on data. For example, the data for an action game might be keys pressed or the position of the cursor when the mouse is clicked. The data for a word processing program are the keys pressed while you are typing a letter. The data for an accounting program would include, among other things, expenses and income. The data for a program that teaches Spanish could be an English word that you type in response to a question. Recall that a program must be stored in the computer's memory for it to be run. When data is supplied to a program, that data is also stored in memory. Thus we think of memory as a place for holding programs and data. One of the nice things about programming in a high-level language, as opposed to machine language, is that you don't have to worry about which memory locations are used to store your data. But how do we refer to an item of data, given that there may be many data items in memory? Think of memory as a set of boxes, or storage locations. Each box can hold one item of data, for example, one number. We can give a name to a box, and we will be able to refer to that box by the given name. In our example, we will need two boxes, one to hold the side of the square and one to hold the area. We will call these boxes S and A, respectively. If we wish, we can change the value in a box at any time, since the values can vary. S and A are called variable names, or simply variables. Thus a variable is a name associated with a particular memory location or, if you wish, it is a label for the memory location. We can speak of giving a variable a value, or setting a variable to a specific value such as 1. Important points to remember are: a box can hold only one value at a time. If we put in a new value, the old one is lost. We must not assume that a box contains any value unless we specifically store a value in the box. In particular, we must not assume that the box contains 0. Variables are a common feature of computer programs. It is very difficult to imagine what programming would be like without them. In everyday life, we often use variables. For example, we speak of an address. Here, address is a variable whose value depends on the person under consideration. Other common variables are telephone number, name of school, subject, size of population, type of car, television model, etc. What are some possible values of these variables? Example: develop the algorithm. Using the notion of an algorithm and the concept of a variable, we developed the following algorithm for calculating the area of a square, given one side. Algorithm for calculating area of square, given one side. 1. Ask the user for the length of a side. 2. Store the value in the box S. 3. Calculate the area of the square, S times S. 4. Store the area in the box A. 5. Print the value in box A, appropriately labeled. 6. Stop. When an algorithm is developed, it must be checked to make sure that it is doing its intended job correctly. We can test an algorithm by playing computer, that is, we execute the instructions by hand, using appropriate data values. This process is called dry running or desk checking the algorithm. It is used to pinpoint any errors in logic before the computer program is actually written. We should never start to write programming code unless we are confident that the algorithm is correct. Write the program for the algorithm. We have specified the algorithm using English statements. However, these statements are sufficiently computer-oriented for a computer program to be written directly from them. Before we do this, let us see how we expect the program to work from the user's point of view. First, the program will type the request for the length of a side. We say the program prompts the user to supply data. The screen display might look like this. Here we have specified what the output of the program should look like. For instance, there is a blank line between the prompt line and the line that gives the answer. We have also specified the exact form of the answer. This is a simple example of output design. This is necessary since the programmer cannot write the program unless he knows the precise output required. In order to write the computer program from the algorithm, a suitable programming language must be chosen. We can think of a program as a set of instructions, written in a programming language, which, when executed, will produce a solution to a given problem or perform some specified task. The major difference between an algorithm and a program is that an algorithm can be written using informal language without having to follow any special rules, though some conventions are usually followed, whereas a program is written in a programming language and must follow all the rules, the syntax rules, of the language. Similarly, if we wish to write correct English, we must follow the syntax rules of the English language. In this book, we will be showing you how to write programs in C, the programming language developed by Ken Thompson and Dennis Ritchie of Bell Laboratories, and one of the most popular and widely used today. Program P1.1 is a C program that requests the user to enter the length of a side and prints the area of the square. It is not too important that you understand anything about this program at this time. But you can observe that a C program has something, a function, called main followed by opening and closing brackets. Between the left brace and the right brace, we have what is called the body of the function. The statement int a, s, is called a declaration. The parts after / are comments that help to explain the program but have no effect when the program is run, and is used to denote multiplication. All of these terms will be explained in detail in due course. Finally, a program written in a high-level language is usually referred to as a source program or source code. Test and debug the program. Having written the program, the next job is to test it to find out whether it is doing its intended job. Testing a program involves the following steps. 1. Compile the program. Recall that a computer can execute a program written in machine language only. Before the computer can run our C program, The latter must be converted to machine language. We say that the source code must be converted to object code or machine code. The program that does this job is called a compiler. Appendix D tells you how you can acquire a C compiler for writing and running your programs. 2. Among other things, a compiler will check the source code for syntax errors, errors that arise from breaking the rules for writing statements in the language. For example, a common syntax error in writing C programs is to omit a semicolon or to put one where it is not required. 3. If the program contains syntax errors, these must be corrected before compiling it again. When the program is free from syntax errors, the compiler will convert it to machine language and we can go on to the next step. 4. Run the program. Here we request the computer to execute the program and we supply data to the program for which we know the answer. Such data is called test data. Some values we can use for the length of a side are 3, 12, and 20. 5. If the program does not give us the answers 9, 144, and 400, respectively, then we know that the program contains at least one logic error. A logic error is one that causes a program to give incorrect results for valid data. A logic error may also cause a program to crash, come to an abrupt halt. 6. If a program contains logic errors, we must debug the program. We must find and correct any errors that are causing the program to produce wrong answers. To illustrate, suppose the statement that calculates the area was written incorrectly as A equals S plus S, and when the program is run, 10 is entered for the length. Below, 10 is underlined to indicate it is typed by the user. Assume we know that the area should be 100. But when the program is run, it prints this: enter length of side, 10 area of square is 20. Since this is not the answer we expect, we know that there is an error, perhaps more than one, in the program. Since the area is wrong, the logical place to start looking for the error is in the statement that calculates the area. If we look closely, we should discover that plus was typed instead of. When this correction is made, the program works fine. Document the program. The final job is to complete the documentation of the program. So far, our documentation includes the following: the statement of the problem, the algorithm for solving the problem, the program listing, test data and the results produced by the program. These are some of the items that make up the technical documentation of the program. This is documentation that is useful to a programmer, perhaps for modifying the program at a later stage. The other kind of documentation that must be written is user documentation. This enables a non-technical person to use the program without needing to know about the internal workings of the program. Among other things, the user needs to know how to load the program in the computer and how to use the various features of the program. If appropriate, the user will also need to know how to handle unusual situations that may arise while the program is being used. Maintain the program. Except for things like class assignments, programs are normally meant to be used over a long period of time. During this time, errors may be discovered that previously went unnoticed. Errors may also surface because of conditions or data that never arose before. Whatever the reason, such errors must be corrected. But a program may need to be modified for other reasons. Perhaps the assumptions made when the program was written have now changed due to changed company policy or even due to a change in government regulations, for example, changes in income tax rates. Perhaps the company is changing its computer system and the program needs to be migrated to the new system. We say the program must be maintained. Whether or not this is easy to do depends a lot on how the original program was written. If it was well designed and properly documented, then the job of the maintenance programmer would be made so much easier. How a computer executes a program. First, recall that a computer can execute a program written in machine language only. For the computer to execute the instructions of such a program, those instructions must be loaded into the computer's memory, also called primary storage, like this. You can think of memory as a series of storage locations, numbered consecutively starting at 0. Thus you can speak of memory location 27 or memory location 31548. The number associated with a memory location is called its address. A computer runs a program by executing its first instruction, then the second, then the third, and so on. It is possible that one instruction might say to jump over several instructions to a particular one and continue executing from there. Another might say to go back to a previous instruction and execute it again. No matter what the instructions are, the computer faithfully executes them exactly as specified. That is why it is so important that programs specify precisely and exactly what must be done. The computer cannot know what you intend, it can only execute what you actually write. C is a middle-level programming language developed by Dennis Ritchie during the early 1970s while working at AT&T Bell Labs in the USA. The objective of its development was in the context of the redesign of the Unix operating system to enable it to be used on multiple computers. Earlier the language B was now used for improving the Unix system. Being a high-level language, B allowed much faster production of code than in assembly language. Still, B suffered from drawbacks as it did not understand data types and did not provide the use of structures. These drawbacks became the driving force for Ritchie for development of a new programming language called C. He kept most of language B's syntax and added data types and many other required changes. Eventually, C was developed during 1971-73, containing both high-level functionality and the detailed features required to program an operating system. Hence, many of the Unix components including Unix kernel itself were eventually rewritten in C. Benefits of C language. 1. As a middle-level language, C combines the features of both high-level and low-level languages. It can be used for low-level programming, such as scripting for drivers and kernels, and it also supports functions of high-level programming languages, such as scripting for software applications, etc. 2. C is a structured programming language which allows a complex program to be broken into simpler programs called functions. It also allows free movement of data across these functions. 3. Various features of C including direct access to machine-level hardware APIs, the presence of C compilers, deterministic resource use and dynamic memory allocation make C language an optimum choice for scripting applications and drivers of embedded systems. 4. C language is case-sensitive, which means lowercase and uppercase letters are treated differently. 5. C is highly portable and is used for scripting system applications which form a major part of Windows, Unix, and Linux operating system. 6. C is a general-purpose programming language and can efficiently work on enterprise applications, games, graphics, and applications requiring calculations, etc. 7. C language has a rich library which provides a number of built-in functions. It also offers dynamic memory allocation. 8. C implements algorithms and data structure swiftly, facilitating faster computations in programs. This has enabled the use of C in applications requiring higher degrees of calculations like MATLAB and Mathematica. Riding on these advantages, C became dominant and spread quickly beyond Bell Labs, replacing many well-known languages of that time, such as ALGOL, B, PL/I, Fortran, etc. C language has become available on a very wide range of platforms, from embedded microcontrollers to supercomputers. There are many languages in the market, which are using to develop applications. Still, C programming language is much popular due to following reasons. 1. C language has less number of keywords, as we know that in a standard version of C programming language there are only 32 keywords and 32 keywords are easy to remember. 2. C language has less number of standard libraries and library functions. Those are well established and standardized portable, but they can be used to design any kind of, almost, functions. 3. C language has rich set of data types with awesome features of type qualifiers like const, volatile, etc. 4. We have already discussed in previous post about low-level and high-level languages. C language is one of the most popular programming languages which are able to make low-level applications like device drivers, operating systems, firmware, etc. along with the high-level applications like desktop applications. Note that, due to this amazing feature, C programming language is known as middle-level programming language. 5. C language is very efficient, popular and well understood. 6. C language is much popular for embedded systems programming due to its flexibility. 7. Programs written in C programming language are easy to read, understand and edit. 8. C language is free, and you do not have to pay anything even if you are using C language for embedded systems. We can easily access any hardware device attached with the microcontroller. Please, don't confuse here. In embedded systems, microcontrollers are like processors. For example, we can capture images through the camera, record videos by writing functions, known as device drivers, for it. 9. C language has other features like portability, modularity, and structure-oriented. Since C programming language is very old language, developed around 1970 to 1972, still it is more popular due to its features.